Hello guys, in this video I'll be showcasing this new side project I've been working on for the past few months. It's an OpenGL OpenTK voxel raymarcher that uses a few optimizations to make raymarching the scene a lot quicker. These optimizations include a compute shader generated BHVH, a MIP level octree, ray caching, which is actually broken at the moment, but whatever, and some temporarily reprojected depth to pay it all off. Before we do anything though, I have to warn you that this is probably the most inefficient GPU code there is, and I assume, as I wasn't able to profile, that there is a bunch of GPU threads being idled up due to lots of workgroup divergence. My code definitely isn't fit for GPU parallelism, but anyways, whatever, right? Let's begin by showcasing the interesting debug screens and the main parameters that affect the raymarcher, and I'll explain the optimizations along the way. You can check the performance of the program by checking the frame graph or the frame timings on the top left. The non-debug view shows us the colored output image of the shader. This is currently using physically based rendering to shade all the pixels but with no image-based lighting, so all smooth surfaces look odd as they only take account the ambient color and not the reflection map. This also shows nice reflections which can be tuned by this parameter to either be perfectly smooth, a roughness of 0, or really rough, higher roughnesses. You can probably notice that as I increase the roughness, the program starts to stutter and lag a bit more. This is because my current implementation of rough reflections is kinda killing the GPU. My implementation just adds a small offset to the surface normal, which causes a bunch of rays within the same GPU workgroup to divert in their directions, which makes it harder for the GPU to do parallel stuff without idling the threads. This is what I understood from looking it up at least. The iterations debug view just shows you how many iterations it took a ray to reach a voxel. I mapped this in the range of 0 to 1, where 0 is black and 1 is white. Now, you want these values to be as small as possible, since that means that the ray took the least amount of iterations, which is a good thing. Now, as I change this max iterations parameter, you can see how the whole thing becomes more white or more black. If I were to show you the colored view, you can see how at low iterations counts, some rays just haven't advanced enough to reach the surface, so they register as if they hit nothing. This is where my main optimizations come into play. Since my voxel texture is a 3D texture, nothing stops us from treating subsequent pixels in lower resolution levels as parent nodes to ones from the higher resolution. Basically, I just treat my MIPs as if they were an octree. This allows me to run my inner cube intersection test on larger pixels instead of the higher resolution pixels, which allows me to hop over lots of big empty space with a lot less iterations than needed. This effect is controlled by the starting MIP chain depth parameter, since that tells the shader at what depth it starts recursively checking the octree. By setting this to 0, we basically disable the optimization, and you can see how the iteration view starts to look a lot more like a proper naive raymarcher with a fixed distance. We'll keep it enabled at max for now, though I have noticed some cases where starting at a lower level actually tends to help performance compared to the max level. I figured out why this was the case, and the following optimization is implemented to try to remedy this problem. So let's see. Ray caching optimization. I noticed that sometimes the ray doesn't necessarily have to start at root node of the octree, the MIP level with only one pixel. It can sometimes start at a higher level than that, saving us a few redundant for loop iterations. As I was drawing this out on a board at school, I noticed that sometimes, if the ray has the right parameters, you can actually avoid doing all of those redundant iterations and start at an n+1 level instead, where n is the current level of the node of the ray. This is because sometimes the ray enters a sibling of the node it was last in, meaning you will only need to start at one level higher than the sibling, which is the parent level. The main heuristic that lets us know if we can cache this data is whether or not the dot product between the current ray direction and the child parent vector is positive. Unfortunately, this made sense on paper, but when I tried to implement it, well, look for yourself. Doesn't seem to be working, is it? I actually have no idea what this doesn't work. Probably my implementation is broken somewhere, maybe an if statement, maybe just a bitwise operation that I missed. Compute-based bounding volume hierarchy optimization. Another major optimization I implemented was a simple BVH that I propagate during my voxel generation step. I just store the AABB min-max values in a singular 64-bit integer, 32 bits for min and 32 bits for max, and I use another compute shader to propagate these values up the MIP chain, back to the root level. For how simple this was to implement, this worked really nicely in conjunction with the MIP level octree optimization. Here's the iteration view with the optimization on, and here it is without. You can clearly see how we save a bunch of iterations when the surfaces are pretty flat. Rotational, positional, temporal, depth reprojection optimization. Every time we finish raymarching array in the computator, I store the color data inside the texture and then bleed it up to the screen texture afterwards. What you can do though is also store the depth of the ray into another texture as well. This, for example, could allow you to take a screenshot of the current scene from the perspective of the camera, and assuming the camera doesn't change position or rotation, re-render the scene much faster. This is because we already have the depth information for each pixel, so we could just advance the array for that pixel by that exact depth, and that literally skips over all the iteration steps we ever needed. Now, there are very big caveats with this idea. For example, you can only do this for a static scene where the voxels never magically get closer to you, and obviously where the camera doesn't move or turn. This is where the reprojection part comes in. By keeping track of the view matrix of the camera during set snapshot, we can reproject the rays coming out of the camera into the frustum of the old camera. Now, this would only work for rotational reprojection, since taking the position is a whole different ordeal, but for now we can at least rotate the camera freely and get the benefits like we did before. As you can see, if I lock the old camera matrix and show you the debug depth view, you'll notice that the reprojected depth looks like we have a big plane in front of us containing the old data, and we're just looking into it from the point of view of the camera. This works fine for rotations, but the moment the camera starts moving around, the whole thing breaks down as I don't take account of the position offset of the old new camera matrices. I forgot to mention this in the voiceover, but the performance boost we get from this temporal reprojection is actually pretty nice. If you look at the iteration view, this is what it would look like without the temporal reprojection, and this is with. As you can see, we're skipping a lot of these iterations on top because we store this depth data. And over here, you see how it's more black, which means less iterations were used, which is a nice thing. Now, as I said in the voiceover as well, when you move, the whole effect breaks down, but that's for the next optimization, which is the positional reprojection. To handle such cases, I've just looked up online if there were any people that implemented this sort of reprojection, and it seems there definitely have been. I've stumbled across this video by Comrade Stinger that showcases asynchronous reprojection within the Unity game engine. Apparently this sort of technique is widely used in the VR scene, and it seems that even Steam VR has support for it through the time warp option or something like that. In any case, here's the important part. At 1 minute and 10 seconds, you can see how they lock up their camera matrix and actually move within the captured volume. It looks like they're using a step-based approach to do the visible stepping in the reprojected color data, but even then, this is extremely cool stuff, so credits to them. So I knew that the algorithm that I had to implement had to use some sort of loop and a fixed step size, which seems oddly familiar to how raymarching was implemented, so I tried just that. I just do another raymarch through the old volume depth data, continuously comparing the old and new depths to check for intersection. For such a stupidly naive implementation, it worked fine most of the time. I'll showcase this by enabling the reprojected depth debug view, and like they did in the video, move through the old volume. Yeah, pretty cool, right? I also have the same issue that they did in the video, in that I'm using a step-based approach, so the steps are visible, especially when you look at the volume at a perpendicular view. I can even change the number of steps using this parameter over here. As I lower the number of steps, you can see it becomes more step-like, If I increase the number of steps, it looks more smooth, but at a performance cost, as you can see from the frame graph. If I were to unlock the old camera matrix and disable the debug view, you can see that it definitely gives us a small performance boost. But compared to just simple rotational reprojection, the positional one is more costly due to the loop and such. Not only that, but sometimes the effect breaks down and some of the depth information gets lost in the process, causing these visual patches that you can see here at low step counts. I'm currently thinking of ways to improve on this because I feel like there's a lot of untapped potential from assuming that the scene is static and that the camera only moves in a specific way compared to the old matrix and the new matrix. So I'm going to keep working on this, and hopefully I'll try figure out new algorithms and ways to improve on it. And another final note before the outro. I know that you can't notice the performance impacts that well in the video since I locked the FPS of the program to 60. This is actually because OBS, like the GUI of the program starts flickering and it's not a really pleasant experience when recorded, so I just had to lock it to 60. But when I tell you that there's a performance impact or a performance boost, you'll just have to believe me because I've done the real life testing, and sometimes the FPS can go up to 140 or as low as 10. So you could just download the project for your stuff and test based on your hardware if you want to as well. But yeah. Anyways, I'm actually in the process of converting this project into a Rust GPU project where you write the shader code in Rust, which sounds very fun. Hopefully you found this video interesting as well, and if you're looking to read on more on how I implemented this, you can look on my website as I wrote a blog post about this with code snippets and stuff. Thanks for watching guys, and yeah, see you in the next one.